vast and limitless at first sight.
3, 2, 1, fire!
To quench our thirst for knowledge, study our planet and communicate, mankind has sent thousands of satellites into orbit around the Earth.
Satellites are absolutely crucial in our daily lives. They're everywhere.
But each time a satellite is launched, debris is jettisoned into orbit. Since the beginning of space exploration, this waste has accumulated, and the situation is close to running out of control. Flying junk is a danger to all other satellites and all future space missions.
We're generating debris faster than it can clean out by the atmosphere.
Sooner or later, there will be so much garbage in space that we cannot use it anymore for our satellites.
To avoid our space dreams turning to nightmares, we need to start cleaning up space. I'm not a moment too soon. Since the end of the 1950s, mankind has launched thousands of satellites into space. Rockets place satellites in orbit, where they follow an elliptical path around the Earth. They circle above our heads at incredible speeds for several years and undertake precise missions. For example, photographing the Earth to establish weather forecasts, relaying telephone, television, and radio signals between two locations on Earth. Or, in the case of military satellites, spying on other countries. Controlled from the ground, they are equipped with computers, cameras, and sensors. Fuel, batteries, and solar panels provide the energy required to accomplish their missions. Some break down, while others stop working when they run out of power. They become orbital debris, circling the Earth at over 17,000 miles per hour. Sometimes they hit other objects, generating thousands of smaller pieces. Today, nearly 1 million objects larger than half an inch have been counted. Being struck by orbital debris is a constant threat for all our satellites, and risks sending our society into the past if nothing is done about it. The problem began 60 years ago. At the end of the 1950s, mankind realized that Earth's future was contingent on space. In the middle of the Cold War, the Soviet Union triggered the space race when it launched Sputnik, the world's first satellite. At the National Center for Space Studies in France, rocket scientist Christophe Bonal evokes the origins of the problem.
The orbital debris problem started at the same time as the first launch on October the 4th, 1957, with the launch of Sputnik 1.
After 21 days, Sputnik stopped working.
It was a non-functioning artificial object, what we call orbital debris.
Sputnik's brief existence came to an end when it disintegrated in the Earth's atmosphere 3 months after its launch. But the small satellite had global consequences. Determined to catch up with the Soviets, the Americans created NASA.
The Soviets' advance was extremely important to astronautics. The Soviets had all the firsts. First satellite launch, first person in space, and they raised the bar for the Americans, who had to increase their missions in order to catch up.
The Americans launched a series of 17 consecutive manned missions, named Apollo. At the time, nobody was concerned about leaving waste or even radioactive elements in space. From 1967 to 1988, the Soviet Union launched spy satellites fueled by nuclear reactors. But some of these satellites were defective. In September 1977, American radars noticed that Russian satellite Cosmos 954 was making erratic maneuvers. It was the first nuclear alert in the space age. On January the 12th, 1978, the Americans contacted Soviet authorities regarding the satellite. 2 days later, the Russians confirmed that they had lost control of their device. When the satellite re-entered the atmosphere, it scattered radioactive material all over northern Canada. The newspapers were quick to report the demise of the Russian satellite in North America. In the midst of the Cold War, it soon became clear that orbital debris could be a potential danger to the population on Earth. But it wasn't the only danger. Even launching satellites into orbit creates debris.
Each rocket launch has left debris in orbit. Old satellites have stayed up there, and that's what has led to the situation we find ourselves in today.
During the years of the space race, satellites were not the only items put into orbit. European Space Agency engineer Radioactive has analyzed the orbital debris created by rocket launches.
When we launch a satellite, the first stage of the rocket provides enough energy to go 10 kilometers in altitude, and then it falls back into the ocean. The last stage takes the satellite into orbit, but then it also stays in orbit itself and becomes debris.
The upper stages of a rocket, along with fuel tanks and nose cones, are systematically left in orbit. Over the last 60 years, much of this debris has accumulated, while some has disintegrated. Working alongside the European space agencies, space scientist Noelia Sanchez-Ortiz analyzes the circumstances and the destiny of orbital debris.
Space debris come mainly from satellites that we have put in space. Once they stop working, historically we leave them there, and they remain orbiting around the Earth unless the satellite is placed in a very low orbit, and then it ends up falling in our atmosphere.
At low altitude, debris moves at speeds of 18,000 miles an hour. But the Earth's atmosphere gradually slows it down, and when pieces eventually fall to Earth, they are mostly destroyed. The air molecules are compressed by the speed of the debris, which creates heat and eventually combustion, causing the pieces to break up. During the day, there is little to see, but at night, this burning waste sometimes looks like shooting stars. Problems arise when this debris does not burn up completely in the atmosphere. In 1997, the 550-pound fuel tank of a Delta II rocket crashed near Georgetown in Texas. In 2001, the third stage of a Delta II rocket landed 150 miles from Saudi Arabia's capital, Riyadh. In 2011, the nose cone of a Soyuz rocket was found in Martinique. And in 2013, several titanium tanks appeared in the garden of an electrician in Texas. So far, nobody has been killed, but it's merely a question of time. In September 2016, the second stage of a Falcon 9 rocket crashed into an outbuilding on a small island near Java. It seems that sometimes the sky really does fall down. Since orbital debris poses a threat to the Earth's population, it is now catalogued and the risk evaluated.
Currently, we estimate that there are about 36,000 objects orbiting the Earth. We can add the 30,000 or so objects that have already fallen back to Earth.
And they will stay there for some time. Since all rocket launches, including military operations, are monitored, it is relatively easy to know what is circling above our heads.
All the artificial objects in space, satellites and debris orbiting above our heads, represents a mass of around 9,000 tons. To give you an idea, the Eiffel Tower is 7,500 tons, so a bit more than that.
In the vast area that is space, an Eiffel Tower's worth of small scattered pieces is more like a cloud of dust. So, in order to show a representation of the debris, we need to enlarge them. In real life, the pieces are considerably smaller. The suburbs of our planet contain a mixture of working satellites surrounded by circulating waste. But the suburbs are nonetheless organized. Satellites around our Earth use 3 different orbits. Furthest from the Earth is geostationary orbit, a thin layer 22,000 miles away. Satellites in this orbit remain constantly above the same point on the equator and provide our telecommunications, telephone and computer link-ups, and television broadcasts. Each satellite is spaced an average of 40 miles apart. With space at a premium, satellites need to be removed when they have served their time. Their last fuel reserves are used to deorbit them to another area. Here, the satellite is moved higher to a graveyard orbit, further from Earth, where it will not interfere with anything. Medium Earth orbit, situated between 1,200 and 22,000 miles in altitude, is avoided. This vast zone is occupied by radio navigation satellites, like Galileo. If one of these satellites breaks down, it is placed into an intermediate orbit where it will not interfere with any others. But if it runs out of fuel, nothing can be done. Finally, The closest orbit to Earth is known as low Earth orbit and is situated below 1,200 miles in altitude. This is where the last 60 years of space exploration has left the most debris. And the only way of getting rid of debris in this area is to send it into Earth's atmosphere, where it disintegrates.
There are different areas on Earth where objects can re-enter with almost no risk because they are far from populations. For example, there is an area in the South Pacific which is very, very big, and where we tend to re-enter large objects.
If the satellite still has fuel, it is possible to control its movements in low, medium, and geostationary orbits, as long as it is still functioning. But some satellites can hurtle out of control even if they still have fuel.
One of the problems we have with satellites is that from time to time they break down, and we don't know why. They worked on Monday, Tuesday, Wednesday, and on Thursday, bam, broken. And we've had no warning. There's been no sign that anything was wrong.
Satellite operators are loath to talk about malfunctions for fear of losing credibility. Yet most failures are caused by nature interfering with safety measures.
When we analyze the cause of these malfunctions, it can, for example, be a result of a solar flare.
During solar storms, our sun releases huge amounts of energy that disperses electrically charged particles into space. Earth's electromagnetic field acts as a shield protecting us from particles, visible during the northern lights. But satellites are like sitting ducks. Solar radiation is capable of wiping out navigation systems. And despite being protected with high-tech gold foil, it is estimated that a dozen or so satellites are destroyed each year by solar flares, turning them into orbital debris.
Space is an infinite empty space with some junk moving around above our heads. And these objects pose two problems. First, when they are in orbit, they're there for a long time. For example, an object at an altitude of 600 miles will stay there for 1,000 or 2,000 years. Secondly, during the course of these 1,000 or 2,000 years, they are moving at speeds of 18,000 miles an hour. 18,000 miles an hour for 1,000 years is a lot, so the probability of crashing into something during that time is very high.
Until 2007, experts tracked around 12,000 large pieces of junk. But since then, 3 major events have caused the situation to degenerate. The most serious involved Cosmos 2251, a Russian satellite in low Earth orbit that suddenly stopped working. The Russians could no longer communicate with it and were unable to deorbit it to Earth. In a perpendicular trajectory at the same altitude, a brand new American satellite called Iridium 33 was in orbit. The impact sent debris flying in all directions. Around 2,500 pieces, larger than 3 inches, and many other smaller fragments were ejected into space, posing a threat to all the devices in low Earth orbit. This collision proves that an out-of-control object in low orbit is a danger to all working satellites. Another event worthy of Star Wars took place when China decided to deliberately destroy a weather satellite that was no longer in use, using a ballistic missile armed with an infrared seeker and a warhead. It was an arrogant show of strength by Chinese authorities, with no concern for the consequences. On the 15th of November 2021, the Russians returned fire with a Noodle missile. Its target was a decommissioned satellite called Cosmos 1408. The resulting explosion scattered 1,500 pieces of large debris into low orbit in all directions. These events were arrogant shows of strength by major powers, with no concern for the consequences.
Everybody is talking about the events caused by the Chinese and Russian governments destroying a satellite on purpose. We all now know that these types of events are the greatest source of a risk of collision to our satellites in space.
As a result, there are now more than 1 million pieces of debris larger than half an inch circling the Earth. And some of these pieces come not from satellites, but from rockets.
In the fuel tank of a normal rocket that takes satellites into orbit, you have one chamber with liquid oxygen and another with liquid nitrogen. And I'm sure you remember from school that when these two gases mix, it becomes nitrous oxide, and it explodes. And that's what happens again and again in space. Not all the fuel is used to the last drop. This reserve fuel mixes, and instead of having an intact upper level, you have 1,000 pieces of debris, which remain in orbit.
Like a pandemic, this junk proliferates and risks creating even more debris. This phenomenon is known as Kessler syndrome, in honor of the NASA consultant who described, analyzed, and quantified it.
We currently have enough objects in Earth orbit. Once every 10 years, we expect 2 objects to run together and create a major breakup.
Don Kessler proposed this scenario back in 1978. Since then, it has been proven multiple times.
Like the Cosmos Iridium collision back in 2009. About every 5 years, we expect collisions between some large object and a large fragment to also produce some debris.
Don Kessler also predicted that the collisions would have a cascading effect where each collision increases the likelihood of further collisions.
The issue becomes when this happens, an object can come in and hit the satellite and produce a spray of particles that are very numerous in number for the smallest particles, that those can go on, and because they're traveling so fast, can damage spacecraft. Then you also produce about 100 big enough fragments that will go on and hit another satellite in the same way and break that satellite up. And so you have this slow cascading phenomena going on.
This theory was proven accurate in 1996, when debris from an Ariane rocket launched 10 years before crossed paths with a French military satellite called Cerise. Knocking out a 10-foot stabilization boom and causing Cerise to tumble out of control. This incident is just one example of such a chain reaction in space. Non-functioning satellites and rocket leftovers have created clouds of debris traveling around the world at 18,000 miles an hour, hitting working satellites and creating even more debris. This proliferation could endanger a huge range of activities on Earth. It's easy to forget that satellites are a major part of our daily lives.
We all expect to open our mobile phone and look for a place where we want to go and find the directions to get there. We use satellite positioning technology. In the same way, when we go on a trip, we withdraw money at an ATM in America, and we obtain that money thanks to satellite telecommunications that connect with our bank in Europe.
It's hard to imagine life without smartphones, bank cards, or GPS systems.
Nowadays, we wouldn't live long without satellites.
Yet the proliferation of debris risks compromising today's constantly diversifying satellite services. So all space agencies have to take serious risks each time they launch, including the European Space Agency.
If we are waiting for a situation where our uncertainty volume is completely empty, that would mean we could never launch. So believe it or not, we are launching despite of the possibility of having conjunctions with objects, because otherwise there would never be a green light for launch.
The risk is now proven and even quantified.
The odds of losing a satellite are 5%. Part of it is the risk of being hit by debris. The other parts are simple. There is complicated hardware that can break, causing the satellite to be lost. But the likelihood of losing a satellite can quickly reach 10 or 20% with the increase in orbital debris.
The European Space Agency estimates that the risk of collision will rise to 20% by 2038. So 1 out of every 5 satellites would not complete its mission. It's a huge figure. Space agencies have had to look at ways of negotiating this minefield and detecting the circling waste. Since 1957, the United States has been using a space surveillance network to predict where and when orbital debris will enter the Earth's atmosphere. They have established a catalogue of the debris that is currently in orbit and use this to determine which country owns the debris that is entering the atmosphere. They can also warn NASA if debris is at risk of interfering with their satellites. Over time, as the number of artificial objects in orbit has multiplied, this system has been refined and computerized. But in Europe, a similar space surveillance system was not put in place until 40 years later. In 1996, when debris from the Ariane rocket damaged military satellite Cerise, the French Ministry of Defense created a system known as GRAVE.
The GRAVE system, a space surveillance network, is our main sensor that allows us to detect objects that orbit around 250 to 600 miles in altitude, as long as they are large enough to be detected by radar. In other words, if they are the size of a large washing machine.
To detect orbiting satellites up to 600 miles above France, even when it's cloudy, the system uses a particular radar that makes real-time calculations to follow and anticipate the trajectories of thousands of satellites. The GRAVE system was able to detect 30 or so Chinese and American spy satellites that had not been catalogued previously.
Today, international relations in space are a mixture and an extension of those on the ground. In other words, there is as much mutual aid as there is competition, or sometimes open confrontations.
France agreed to keep quiet about the spy satellites, But in return, they asked the Americans for access to their orbital debris catalogue. This catalogue is considerably more detailed than the European version, since the Americans can detect objects as small as 4 inches.
We deal with the problem of small objects by Franco-American cooperation that allows us to retrieve information even at the confidential level.
This constant space surveillance is efficient and allows civilian and military satellites to avoid collisions with orbital debris. If there is a risk, ground-based operators can move their satellites slightly out of their orbit. These maneuvers happen more and more often, particularly for the largest satellite of all time, the International Space Station. This inhabited satellite is threatened by debris several times a year. To avoid orbital debris with an identified trajectory, the space station has to be moved from its course. In 2012, it avoided a piece of debris from the collision between the Iridium and Cosmos satellites 3 years previously. In 2021, the space station was forced to slalom 5 times between flying junk. This constant threat has become part of the astronauts' daily lives.
The space station is on a collision course with a small piece of space junk, as we've heard from the ground. My watch is beeping as a warning. We have to take the ISS into a higher orbit. For this, we have to turn on the engines for 37 seconds. And that is actually the only time in which we can measure or feel any acceleration on board. Suddenly, we are no longer weightless, but we are pushed backwards by the engines of the space station. So, let's start now.
Sometimes the ballistic data about debris is imprecise, in which case no risks are taken, and the astronauts are told to evacuate the station urgently. They take refuge in the escape module, which can be separated from the station and could return the astronauts to Earth. But evacuation isn't necessary every time. Frequently, orbital debris is not detected if it is smaller than 4 inches. Nowadays, there are around 150 million pieces of junk that are too small to be tracked by radars. In order to avoid this menace, satellites and the space station need to be protected. In Freiburg, in Germany, scientists from the Fraunhofer Institute test shielding material using a super-fast accelerator known as a space gun. This space gun fires tiny metal balls at various shielding materials. This series of chambers reproduces conditions in space. They are filled with light gases and accelerate the balls close to the same speed as orbital debris, 15,000 miles an hour. At this speed, the behavior of collisions is very different from that on Earth, during a car crash, for instance. When a car hits a wall or another car at 30 miles an hour, it is deformed, and thousands of pieces of debris are created as the material fragments. But at hypervelocity, speeds above 6,700 miles an hour, a collision creates different physical phenomena.
In a high-velocity impact, the particle is fragmented. So parts of it are vaporized and ionized, and the other parts can't withstand the really huge pressure loads which we have behind the shock wave.
In hypervelocity, a 1 millimeter ball has more energy than a baseball flying at 60 miles an hour. Reinforced doors protect the laboratory. The high-speed camera, which films more than 1 million frames per second, records the moment of impact. As a safety precaution, no one can stay in the room while the space gun is being fired. The results of these tests on different satellite components are then analyzed.
For the International Space Station, we tested several shields, but we also try to test the components like space solar cells or components like tanks, which are located behind the walls of a satellite.
Using ultra-slow motion images, the Space Gun team manages to understand and model what happens during a collision. Their work allows them to come up with structures that are both light and resistant to hypervelocity impacts. They have just proved that doubling or tripling insulation layers can protect satellite components hit by debris smaller than 4 inches. The first layer fragments the debris. The second dissipates its energy and protects the third layer. Thanks to these experiments, scientists have been able to design satellites that are resistant to small debris. But even today, we are unable to protect astronauts when they are outside their vehicles during spacewalks. They remain exposed to small debris that can't be detected by radars or seen by the human eye since they are traveling so fast. Even a minor impact would puncture an astronaut's suit and lead to instant death. Because of this risk, NASA is actively developing robots that could replace humans to accomplish maintenance operations outside the spacecraft. Though even robots would be unable to withstand a collision with debris of more than ½ an inch. Obviously, the less debris there is, the better. Countries around the world have tried to establish rules for the non-proliferation of large debris, as they have done for land-based nuclear weapons. For example, satellite operators are asked to empty all fuel on board their space vehicles. All rockets are equipped with systems to vent or burn excess fuel, a system that is tested on the ground before each launch. Satellites are limited to a maximum 25-year lifespan in orbit. Finally, objects in low Earth orbit that do not completely burn up on re-entry are steered towards broad ocean areas for their final impact. However, these rules are not always respected, particularly since there is no governing body to police offenders. And as time passes, the amount of junk increases.
We're generating debris faster than it can clean out by the atmosphere. And that's what we refer to as being an unsustainable environment.
There's only one real solution to this problem. Clean out the debris that is orbiting around the Earth.
Well, you have to bring back some of the objects that we've left in orbit.
Based on the polluter pays principle, each country is supposed to finance the elimination of its own debris. Since 2013, space engineers have been creating a new profession: space garbage guy. The idea is to come up with robotic systems that can deal with large pieces of garbage by sending them into a junk incinerator, the Earth's atmosphere. But it's a difficult task, since orbital debris moves like an asteroid, spinning around as it orbits because of gravity. Around the world, laboratories have been coming up with robot satellites that could capture debris and deorbit it. That's what they're working on at the Remove Debris project at the Surrey Space Centre in England.
In a real mission, you'll be dealing with uncooperative debris that may be spinning.
Space engineers use technical terms, but their projects seem more like children's games.
One of the technologies we have on our mission is the harpoon.
It seems unlikely, but the team is developing a harpoon capable of attaching onto a piece of debris in order to drag it into the atmosphere.
In our mission, the Remove Debris mission, the thing we're actually testing is the impact mechanism of the harpoon on an actual target plate.
The team is still at the experimental stage, where it is testing a miniature harpoon on a stationary target. First attempt.
3, 2, 1, fire!
Failed. The harpoon did not leave its sheath because of an electromagnetic problem. Second attempt.
Hopefully the harpoon should be able to impact exactly where you want it to hit.
3, 2, 1, fire!
The trial and error method is a long process, but the team is improving its system. The first full-scale test in space in 2019 was a success.
Hopefully, when that goes into space, because of the lack of gravity, the alignment should be much better than the tests we can perform on Earth.
The trial and error method is a long process, but step by step, the team is improving its system. The first full-scale tests in space will take place in 2020. The harpoon is not the only tool envisaged by space engineers. The South Africa Space Agency, created as recently as 2010, has come up with its own cleaning solutions that it hopes to market later. One of their projects involves building a small satellite capable of unfolding its tentacles to capture debris, hence its name, Medusa.
Medusa will enclose the debris and drag mover to where it needs to be, either to grave orbit or you decrease your altitude and eventually toss this debris back into atmosphere and let it burn up as the re-entry.
Another advantage of the Medusa satellites is that they can be launched in squadrons, as tests from the International Space Station have shown.
Medusa is very light. It's about 175 grams. It is designed to be put onto CubeSats, which is satellite this size.
A CubeSat is a small, multi-use satellite in the shape of a 4-inch cube. Developed by a Californian university, dozens of them can be launched at a time, which keeps costs down. It's a godsend for researchers who have no other way of running experiments in space. Coupled with CubeSats that have already proven themselves, Medusa should be able to eliminate debris over a long period.
At the moment, there's a lot of proposals like harpoons. A lot of them are one use, so you fire it one time, you miss, you miss. The uniqueness of Medusa is that it allows multiple attempts, so the idea is to use it many times as you can to remove small targets.
But the drawback with Medusa is that it only targets small space junk. For large, non-functioning satellites, other tools are necessary, which opens up the problem of financing these operations.
Unfortunately, none of these solutions is ready for use. Nobody is ready to pay the high price necessary to get rid of large orbital debris.
The bigger it is, the more it causes problems because any damage creates more junk. The largest non-operational piece is Envisat, an observation satellite the size of a bus that was launched in 2002 by the European Space Agency. At the time, the agency was trying to get the biggest return from their investment, but today, Rödiger Jähn distances himself from his predecessor's actions.
They just want to maximize the revenue. They use the last drop of fuel for their operations rather than using the fuel for deorbiting, and this is the problem.
When it was built, it was the largest observation satellite ever constructed. After 5 years of activity and having circled the Earth around 30,000 times, it should have been deorbited before the end of its mission. However, 10 years after being launched, the European Space Agency lost all control of Envisat on April the 8th, 2012. Today, it is a ticking time bomb as it crosses paths with many other working satellites. The situation is so critical that the European Space Agency is funding an ambitious program to try and remove Envisat from its orbit.
We believe that throwing a net could be an option, because throwing a net means you will later have a connection by a tether. And that means the captured Envisat inside the net can be pulled.
To test this space net, engineers use an aircraft to recreate space's zero-gravity conditions. At the top of its parabolic flight, in the form of a bell, it releases passengers and objects from Earth's gravity for several seconds. Enough time to test a miniature version of the net they will use to catch an 8-ton satellite. Tests have proved that adding weight to the corners of the net allows it to enclose the body of a satellite without snagging on its fragile solar panel. Now, all they have to do is build a tractor satellite that can retrieve Envisat and return it to port.
Envisat is 8 tons, certainly more heavy than the removal vehicle. When you have to remove something which is more heavy than yourself, it's better to pull than to push, because that gives a more stable scenario.
Though it is essential for space safety, even this project is still in the theoretical stages, for one simple reason.
We have investigated the problem to look for a solution, but it would cost €500 million.
For technical and economic reasons, no robot garbage collector is ready for work at this time.
For this to become workable, the cleanup operation would need to be free, like if it was a passenger on another mission, and what seems to be quite promising is what we call space tugs.
The space tug would be multifunctional, a kind of space-based Swiss Army knife.
On Monday, it would refill a satellite. On Tuesday, it would repair another. On Wednesday, it would inspect a satellite. On Thursday, it would do maintenance. And on Friday, it would return to Earth, and it would gather up a piece of space junk and send it into the atmosphere.
However, according to the Airbus engineers who are currently developing space tugs, some technological problems remain.
What we cannot do at the moment is a scheduled rendezvous with a target that has not been designed for this purpose. For example, an old satellite or a piece of orbital debris.
A space rendezvous is an organized and controlled meeting between two space devices.
We need to develop new autonomous technologies that can manage on their own. They would be based on vision sensors that would scan the environment and analyze the contents of the images they acquire. And this data analysis will detect the parts of the objects that interest us in order to be able to catch them and manipulate them.
The Space Tug project is still being studied, but thanks to major funding, the first efficient cleaning service may come into use by 2025. As well as the European Space Agency and Envisat, space tugs already have other new clients. Private companies are currently sending thousands of satellites into low Earth orbit to create a new kind of network. These projects, known as mega constellations, have already become a reality with satellites like SpaceX's Starlink or the OneWeb project. OneWeb's visionary entrepreneur managed to convince America's internet giants, as well as European Airbus, to make massive investments in the fabrication of a series of hundreds of satellites. Its aim? To guarantee internet access to the most remote parts of the globe.
OneWeb has designed, is building, and will soon be launching a constellation of satellites to bridge the digital divide, provide high-speed broadband access to the half of the world, the 4 billion people without access today. In the initial constellation, we're going to have 882 satellites.
In 2022, the number of mega-constellation satellites in orbit exceeds the number of satellites launched since the beginning of the space race. This has raised concerns among space debris specialists.
Mega constellations are the big thing at the moment. For example, Starlink by SpaceX Elon Musk. Today, he has about 2,000 satellites in orbit in a first generation that will make 12,000, then a second generation that will make 42,000. There is also OneWeb. There are about 500 satellites, and there are many other constellations like this. We expect to have about 100,000 new satellites in orbit by 2030.
Yet the promoters of these mammoth projects maintain that they have taken all the precautions necessary.
There are some things we really need to think very carefully about, and creating some regulatory environment so that the deorbit and the operations are done in a manner consistent with long-term use of space for humanity.
We definitely have to think about how to clean up space debris, but we must also consider the option of imposing a space traffic system in the same way that we have a system for aviation.
There's also the danger that space will be filled with even more garbage. If there are failures, there are satellites that break down, which will then circle around as junk, and that's my concern, that there will be more space debris. It is well known that wherever people go, they leave rubbish in their wake.
We know where the ISS is. We know where our satellites are. We've done a lot of internal resiliency and redundancy to make sure we have control and management of our satellite for the deorbit phase.
Despite reassurances from their operators, mega-constellation satellites do sometimes stop working.
Today, with all these new satellites that we're sending into space, thousands, tens of thousands, hundreds of thousands of satellites, there's no problem, as long as they work.
But there are currently no international regulations in place.
The solution would have to come from above, from the United Nations, legislating and forcing people to get involved in cleaning up the space debris.
Yet most of the people engaged in space exploration claim to be advocating for policies.
We're concerned there is no global body that regulates this. It's a bunch of different groups thinking about regulating it, a bunch of different countries that have a variety of thoughts about regulation without actually putting meat on the bone.
The future of the space industry is promising. But on the contrary, the future of space orbits is more worrying. There are more players putting satellites into orbit. Not just large nations, but also smaller nations that have this capacity, their governments and their private companies.
While waiting for space to apply the polluter pays rule, orbital debris is a major concern for satellite operators. And although few people on Earth are aware of the problem, one day soon, our lives could be spinning out of control.